Welcome to our class today, Wednesday, March 23rd, 2022. We are approaching the end of term. Today we will go to the handout 10, which is talking about Introduction to Computational Complexity, the classes P and NP. And those classes will be introduced. I'll share my screen. Can you see my screen, guys? Thank you, Megan. Thank you, Brandon. So, what do we mean by computational complexity? To connect our previous handouts with the upcoming 3 handouts, so we concern ourselves with issue of decidability and recognizability. What is computable theory? In theory, we now turn our attention to a related subject. What is computable in practice? So what could be computed? What cannot be computed? Is it decidable or recognizable? What is recognizable? What is decidable? So computational complexity is an area of study that asks a simple question: how the computational requirement of a problem grow relative to the input size. You know, sometimes I have 1 input, 2 input, 3 input, multiple inputs. So how the computational process will grow when the input size is growing? This is the question of complexity. From this point forward, we'll be focusing on a problem that are decidable. So these problems are decidable, not just recognizable, because we said each decidable is recognizable, but not each recognizable is decidable. As we will see, however, solvable in theory does not imply solvable in practice. You might see a problem it's solvable, but once it's come to computation or to computers or to machine, it's not solvable. We will see. Computational requirement. We have time, memory, circuit complexity, cost, etc. What do we mean by computation requirements? There are a number of ways that could quantify the requirements of computing based on time, in memory, in circuit, cost, available machine, etc. Our main focus for the rest of this course will be time. So we'll consider the time complexity. We'll not go deep in memory circuit, those mainly for engineers or hardware engineers. So in software, we concentrate on timing. And in this course, specifically for software engineers or software engineering student, we will take or talk about the complexity of timing till the end of this course. How does the running time and an algorithm grow relative to the size of an input argument? So we'll see how the algorithm and the time to run this algorithm and get the results. How it's a grow? It's a grow based on the input size. Running time. What do we mean by running time? How do we measure running time? We define it in terms of how many steps a Turing machine takes to decide the problem. So, definition 1, running time. The running time or time complexity of a deterministic Turing machine, DTM, deterministic Turing machine. M is the function T, n to n, where T of n is the maximum number of steps that the Turing machine M takes on an n character string. Notice that our definition of running time is framed in terms of the worst case scenario. So that normally we took the worst case scenario to represent the running time. Now we will be introduced. I know that in data structure or other courses, you have an idea about this term. Now, Ardia, we talk here that memory, what you are talking about is the complexity when the memory is a factor that we are measuring. But in this course, we'll not consider the memory. We consider the number of steps that the program must take to arrive at the solution. This will be based on the size of input. Normally, when we talk about running time, we are talking about the worst case scenario, which is the maximum number of steps that the program must take. We'll not touch the memory. Don't make things complicated. Is it clear? Of course, multi-tab would be more complex. With multi-processors, which is the circuit complexity, it would be more complex. But we'll talk about time. Just this is the factor. So we ignore the others and we talk about the time. Okay, so what is the big O notation? The big O notation, we need to review it because in data structure and algorithm design, we talk about this. Let f, g be functions. We say f of n equal big O of g of n if there exists a constant c and a threshold n naught, such that for every n greater or equal to n naught, we have f of n less or equal c multiplied by g of n. In other words, f of n equal the big O of g of n if g grows as fast or faster than f. We will see now. What is the consequences of using the big O notation as a running time complexity? Suppose that we have algorithm, we call it A, that solve a problem in a big O of n complexity. Big O, f of n equal big O of g of n, which is n itself, time. What we call this? This will be, as n increased, the complexity will be increased, right? So we call it a linear increase in input size result in a linear increase in running time. How much input I have, how much the time will be increased in the same manner, in linear increment. Now consider another algorithm B that solves the same problem in different way, which has the big O 2 to the power n time. Here, a linear increase in input result an exponential increase in running time. So we write the code in a way it's more complex. It requires more steps. This is what does that mean? So if we increase the number of input, then the running time will be increased exponentially. So here, in the first example with algorithm A, if we have O to 10, then Fn will be 10. If O to 15, then it will be 15 for the Fn. But here it will be 2 to the power 15, which will be a way more running time. Question: which algorithm is faster? Please answer. What do you think, the first one or the second one? The answer in the slide. So the linear function, it's to grow more slowly. Yes, the first one is faster. Thank you, Tammy. It grows more slowly than exponential function, and we know this from math. But from definition, all we are guaranteeing is that there is some crossover point n0, n naught, such that for n greater or equal of n naught, but what if all the real world instances of the problem exist in a region where n less than n naught. What will happen? Think about it. Just because the complexity of one algorithm or a problem is less than another doesn't mean it's faster to solve in all cases. There are situations, though not many, where an exponentially growing algorithm is faster than a linear growing algorithm for real-world instances. So, while there are counterexamples where a hard problem might be easier to solve than an easy problem, ultimately, we are focused on the hardness of the problem in general. So, there are some hard problems. They are easier to solve than easy problem. What do you mean by easier? Less time. So some problem with exponential big O, in some real world cases, it would be solved faster than the one with linear. However, we consider the linear one are easy and the exponential one are hard. So we are focused on the hardness of the problem in general. So definition 3, time complexity, D time, we call it D time. Let T take us N and output R plus be a function. We define the time complexity class D time of T of N to be the collection of all languages that are decidable by a deterministic Turing machine in a big O of T of N steps. This is just, we summarize what we were talking, the definition. So I'll not go and put your hand very deep in math in this matter. So we will give some common running times. Here are some forms of T of running times. So if we have a constant as an input, it would be big O of N. For integers is even problem. So we input integer and we found if it's even. So one step to decide. Logarithmic. So it's big O to log of N. For example, binary search. If I ask you to do a binary search, the complexity of the general binary search algorithm, the known one in box, it is big O to log of N. Linear, we call the big O is linear. For example, big O of N, smallest item in an array, to find the minimum or maximum item in an array. So it would be big O of N, which is the worst case scenario, that the minimum number or the smallest item would be the last item in an array. And we said that we always considering the worst case scenario. Okay. Lean arithmetic, which is big O of N log N. So here we have linear, then logarithmic. For example, the merge sort. The merge sort, and you remember that from the data structure course. Quadratic, which is big O of N, like bubble sort. Bubble sort. Polynomial, big O la poly of N, like a greatest common divisor, GCD. So the algorithm to find the GCD is polynomial complexity. Sub-exponential. Brandon, what do you mean by explain bubble sort? You don't remember it? You mean the algorithm of bubble sort? Okay, we'll talk about it later. Okay, we'll talk about it later. So sub-exponential, which is big O, 2 to the power log n. And here, like factoring, if you are factoring a number or an array. Exponential, big O to 2 to the power poly n, like brute force search. So we are not in a data structure course, but however, the bubble sort is the most common one. And here, Brandon, let me just open something so you can see a figure. Bubble sort algorithm. Wiki, yes. Okay. In a bubble sort algorithm, for example, it has a complexity of big O to n square. Why? Because in worst case, the best case scenario here is to have the array or the list that you are sorting is already sorted. So here you have the minimal number of comparison. But if it's unsorted, and you have to take all the rounds because you have a nested loop in the bubble sort. So for example, if we have an array or a list of number 5, 1, 4, 2, 8, how the algorithm of bubble sort work? At the beginning, at the first step, we check the first two numbers, 5, 1. We move the minimum one to be, we swap them. Since 5 is bigger than 1, we will swap them. So it will be 1, 5, 4, 2, 8. Next step, we will swap the 5 and 4. We move in the list. So it will be 1, 4, 5, 2, 8. Then we will swap between the 2 and 5. Then it will be 1, 4, 2, 5, 8. So the first round, 5 and 8, we will compare them. However, 5 is less than 8, so we will not do any swap. So now we reach in the first round of bubble sort 1, 4, 2, 5, 8. Then we will do second pass. So we have a nested loop in bubble sort. First, we compare each two numbers. We'll start at index 0. For example, here it's 1, 2, 3, 4, 5. So we have from index 0 to index 4 in the array. We'll check index 0 and 1. If 0 is bigger than 1, we swap. Not, we will remain them. Then 1 and 2, then 2 and 3, then 3 and 4. Done with the first round. Then we'll do again. We will start again from 0 and 1, 1 and 4. Do nothing. Sorry. Then 4 and 2, we'll do a swap. 4 and 5, no swap. Here. 5 and 8, no swap. Then the third pass. Now you see here it's sorted. But based on the algorithm, then we have to do the final step. 1, 2, 4, 5, 8 will do nothing, then the list is sorted. Is it clear what do we mean by bubble sort? Yeah. So with worst case scenario, if you see here, we move from 0 to 4 in the inner loop, and in the outer loop from 0 to n minus 1, n equal 4, so from 0 to 3. So we do 3 passes. That means with the maximum number, it's n minus 1, we ignore the 1, and in the inner loop, it's n, so it will be big O of n squared with average complexity, or a worst case, we call it, or an average complexity. With the best thing, if it's sorted, we can stop, then it could be O n log n, or even other n big O to n squared. So that's what we call it by bubble sort. It's n plus n, so normally we don't make big O to n, so we'll take it big O of n. Is it clear now? Okay. Now, we have some basic complexity classes. The complexity class P is defined as all problems solvable by a deterministic Turing machine in a polynomial time, which equal P equal for all deterministic Turing machine that have a time complexity n to the power k, where k is greater or equal 0. And this, the U means union, because we said it's all problems solvable by a deterministic Turing machine in a polynomial time. P equal, this is the class P, the union of all deterministic Turing machine for a polynomial complexity where we have at least 0 or more cases, problems. Okay. The class EXP, which is the complexity class, EXP is defined as all problems solvable by a deterministic Turing machine in an exponential time. Here, polynomial time, P. EXP, exponential time. You know, it's like abbreviation of the class. Polynomial, exponential, which is the union of all cases, which will be 0 or more problems that's solvable by a deterministic Turing machine in an exponential 2 to the power n to the power k. So then P is a subset of EXP, which is a subset of deterministic Turing machine complexity or running time. So the relationship between basic classes, that P is a subset of EXP. Clear till here? Questions? Okay. From the beginning till the previous slide, we are talking about deterministic time. Okay. Here, if we want to write this function or complexity in an exponential format, what does that mean? It is n to the power k to the power 1, right? Right, Tammy? So this is a subset of this one where k equal 1. But so the polynomial one is a subset of exponential one, because this could be 0 or more. So P, the class P polynomial, is a subset of the basic class exponential complexity running time for deterministic Turing machine. Is that clear? Okay, you are welcome. So now we'll start talking about non-determinism. So far, we've considered the running time of deterministic Turing machine. What about determinism or non-deterministic ones? So recall the non-deterministic Turing machine NTMM decide the language L for all string sigma that belong to the alphabet sigma star. Every path M takes on W halts. W belongs to L if and only if at least one path accept. W is not belonging to L if and only if every path reject. So this is the non-determinism. It is recognizable but not decidable. You remember that from the previous class. So every path W halts by accept or reject. How? If the string W belongs to that language, if and only if there is one path, accept. W is not belong to that language if every path reject. If and only if. This is the meaning if if and only if. So what is the running time for non-deterministic problems? The running time or time complexity of a non-deterministic Turing machine NTMM, its name M, is the function t n to n, where t of n is the maximum number of steps n takes in every computational path on any n character string. So as you know, same as DFA and NFA. In DFA we have one path and we go only one path. In DFA we have multiple paths that running in parallel. So the complexity in non-determinism, it's the complexity of all possible paths, whatever it's accept or reject, because we have more computation going on. Here again, running time is defined in terms of worst case scenario, that the problem will go in each possible path. So let t equal n to r plus be a function. We define the time complexity class n time. Before we use d time, now n time, t of n, to be a collection of all languages that are decidable by non-deterministic Turing machine in a time complexity big O of t of n steps. Now, the issue here, what this will be: constant, linear, quadratic, logarithmic, exponential, polynomial. We will see. The class NP. The complexity class NP is defined as all problems solvable by a non-deterministic Turing machine in a polynomial time, same as deterministic. But here, when we calculate, we have n to the power k. So it's polynomial, but we call it NP because it's non-deterministic, multiple paths or multiple paths. And NEXP, it's the same, but if we have 2 to the power n to the power k as exponential function. So NP is also a subset of NEXP, same again as I explained to Temi, that consider n to the power k to the power 1. So the class P polynomial is a subset of exponential, and it's a subset of non-deterministic time frame. And these are the two basic classes for non-deterministic finite time complexity. And for deterministic finite complexity, we have the class P and EXP. Okay. So here the running time, if it's deterministic, we have one path. If it's non-deterministic, I can go to this path, this path, this path. So I have to calculate all the complexity of all possible paths that the program might follow. Questions? Questions? Is it clear now, the class P and P? Class P, EXP, NP, and NEXP. Yes, all routes. Yes, Brandon, you are correct. Do you remember the DFA, the NFA at the beginning of the course? The same concept. So now, if the problem is NFA, then we have to use non-determinism complexity. If it is a DFA, deterministic finite automata, and I have to go in one path, even if the like DFA has, if I go from here, I'll continue. So I'll go one path. But here I might go this one and go to this state, here to this state or accept the state. So if there is one accept state, then it's non-determinism. Clear? We'll have more examples. We'll have more examples. Don't worry, Ardia. We'll get more examples. Now, let's go back. Here. In this handout, here are our examples. This is deterministic. So if I receive 1, I'll go here. If I receive a 1, I'll back here. If I receive a 0, I'll go here. Then I receive a 1, I'll go to end state. So it's one path based on the input. I will follow one path. But with NFA, if I receive a 0, I might go to this path or I go to here. So I have two paths here. So I have more steps that the program will take. And as I told you before, that the program will do this in parallel. So it will consider this path with 0 and it will return it to Q0. At the same time, it will consider that the 0 will move me to Q1. So this will add more computational time to solve the problem. Is that clear? Here's the difference between determinism and non-determinism. For example, for the symmetry, like here. So if I have a 0, I'll go to Q0. This is the path. Then if I have a 0, I'll go to Q1, or either I can stay at Q0. Then I receive a 1, I stay at Q0. Then I receive a 0, I stay at Q0. Then 1 at Q0. But this path is rejected. I don't reach to final state. So all these possible, we said they will be run in parallel. So they will add more time and more complexity, more running time to solve all possible paths. Is that clear? It's the same as this tree. This is what do we mean by paths. Okay, Ardia, is it clear now? Yeah. Now, the class NP complete and the $1 million question. Here we have a $1 million question. Here, complete NP complete. What is the NP? Back to the handout 10. I need you to connect your ideas. Here is the NP, non-determinism, polynomial. So we'll talk about this class, NP complete, and the $1 million question. What is the $1 million question? Does P equal NP? Does deterministic polynomial running time complexity equal non-deterministic polynomial time? Yes or no? This is a $1 million question. P versus NP. How do P and NP relate? What is the relationship between P and NP? Mathematically, in definition, they look the same, but this is non-determinism. This is 2 to the n to the power k. And here for the P, it's also deterministic time for n to the power k. But here P, deterministic time, and here it's NP. So what is the relationship between those two classes? First off, we know that P is the class of problem solvable by a deterministic Turing machine in a polynomial time. Informally, it is the class of problem that can be solved quickly. This is informally. So it's quick for computers. NP is the class of problems solvable by a non-deterministic Turing machine in a polynomial time. Informally, it is the class of problem to which a proposed solution can be checked quickly. So, what is the difference? Can be solved quickly. Here can be checked quickly. Think about it. What is the $1 million question? The first thing to notice is that P is a subset of NP. Recall deterministic Turing machine are ultimately a subset of non-deterministic Turing machine. And we proved that before also. Any DFA, deterministic finite automata, there is an equivalence NFA that do the same, right? We proved that mathematically also. So whatever a deterministic Turing machine can solve in a polynomial time, a non-deterministic can solve in a polynomial time. Now there are two possibilities. The answer, there might be P not equal NP or P equal NP. There exists a problem solvable by a non-deterministic Turing machine in a polynomial time, for which there exists no deterministic Turing machine that can solve them in a polynomial time. If this is the answer, the case. If this is the case, every problem solvable by a non-deterministic Turing machine in polynomial time has an equivalent deterministic Turing machine that can solve it also in a polynomial time. Which one is the correct answer? Let's go P versus NP. So which is it? As it turned out, this presently the greatest open problem. We have set of a greatest problem in computation. If you click in this one, P versus NP problem, this is the example, this is the entry, and NP completeless. Harder problems in NP not known to be in P or NP complete. So there are problems is not solvable till today. So this is what we called, if you want to read more, you can just click on this pink words and you will find the full explanation. In computer science, still open problems, open for study and research. If you can solve it, you will get $1 million. In fact, the Clay Mathematics Institute is offering $1 million for a solution. If you find a solution, you will get $1 million. Although we still don't know, but many people believe that P is not equal NP. So we don't know which is the correct answer. However, there are some computer science scientists and people or professionals, they believe that P is not equal NP. 100% correct answer? We don't know yet. It's one of the open problem in computer science. Okay. Okay. Now we're back to NP alone. So I cannot say that P is a subset of NP or P equal NP. Don't know the answer yet. Okay. Factor. An example NP problem. We'll take an example of non-deterministic polynomial problem. By fundamental theorem of arithmetic, you need to know more, just click on this. It will take you to the Wikipedia and explain for you this theorem. Every integer greater than 1 can be expressed as a unique product of prime numbers. Can such an integer factoring is the process of recovering the associated prime factors? In its basic form, factoring is not a decision problem. So let's restate it as one. Factor n greater, b greater. If n has a factor f, for f greater than 1 and less than b, return true, else return false. For example, the number 11. How many factors for the 11? 11 and 1. But 10 has 1, it has 2, it has 5, and 10. Right? So theorem, factor equal or belong to NP. Proof. Factor as stated above is a decision problem, and if factor belongs to NP, then there exists a polytime verifier for it. Let verify the factor be defined as follows: n greater than, b greater than, and c. If b divides n, return true, else return false. So if n can be divided by b and there is no reminders, then return true, else return false. A clearly verifying factor is a verifier for factor if c is a certificate for a factor. For example, is a factor of n below bound b? Verification factor will identify as such. It also clearly runs in a polytime. Checking if a divides b can be done with the well-known polytime, which we call it Euclidean algorithm. What is the Euclidean algorithm? You can read about this. I'll not ask you about it. So this is why we study this. You will ask me why we study this. Next year, you will have the information security course, and they will talk about the RSA in a crypto system and the cryptography. So you need these things. So these are a computational problem that came out with the security issue and networking and data communication. So the difficulty of factor is central to the security of RSA crypto system. Upon much of the communication or internet communication security is based. Currently, the general number field sieve is the best known algorithm for integer factorization running in sub-exponential time. It's not sub-exponential time, which is O to the power 2 over 64 over 9 times 3, then big O of 1, log n to the power 1 over 3, log n to the power 2/3. And if you use the RSA of 128, it would be different. And now they start talking about larger RSAs. So the problem is growing. The GNF is rather difficult to comprehend. So the somewhat slower but much simpler quadratic sieve is a good place to start if you are interested. The link gives an intuitive example. So if you want to read about the quadratic, it's out or beyond our course scope to explain RSAs as a problem. But if you see how much the problem will be a bit more complex. If you use a quadratic, it would be simpler, however slower. And as I told you, sometimes doesn't mean that longer time means easier, more complex. It could be simpler but slower. And simple does not mean that it's a short time. Now, the hardest NP problems, and we call it NP completeness. So next classes, we will have class notes and examples on those, so the idea would be more clear. And if you see the group assignment, also taking these problems into consideration. NP completeness. Now that we have seen a number of NP problems, we are starting to get the sense that some problems might be harder than others. For example, multiplying two integers is easier than factoring their product. So it would seem based on our state-of-the-art algorithms. A natural question came out: are some problems in NP fundamentally harder than others? Although we cannot answer this until we settle the P versus NP question. So we don't know the answer. We can ask a related question. Are there problems in NP that are at least as hard as every other problem in NP? This is what we can ask. At first, this might seem like an unsatisfying question. I know this kind of question, maybe you never think about it, but it's available in computer science problem and software engineering problem. If we don't know if some problem in NP are fundamentally harder than others, because we don't know if P equal NP, then what does it really mean to talk about some problem being at least as hard as all the others? We'll say this problem is hard like other problem. The idea is we are placing an upper bound of the hardness of NP problems. If we can prove problem X belongs to NP is at least as hard as all other NP problems, then we know that problem Y belongs to NP is no harder. Clear, or you need more clarification, guys? Okay, we have this class P. Here, NP complete is shown as a region inside NP where the hardest problem resides. So we have the P. This is what the most believe, that P is a subset of NP. And here, within NP, we have a subclass called NP complete. So we don't know the answer if P equal NP, right? We don't know the answer. It's a $1 million question. To simplify the idea, we cannot say this is harder than P. Or we don't know if there is a problem, of NP are harder than others. But what we can ask, we can say that we'll make upper bound, the NP completeness as an upper bound that allow us to prove that the problem X, which belongs to NP, we know that it's NP, is at least as hard as all other NP problems. Then, if this, we can prove this, then we know that problem Y that belongs to NP is not harder than X. Is that clear now? Yes, tell me the hardest problems are lie down NP completeness. So the class NP complete. NP complete is a subclass of NP, where the hardest problem are residing there, containing problem that can be shown to be at least as hard as all other problems in NP. The problems in NP complete are related to the complexity of entire class. If P equal NP, then we have to find the polynomial time algorithm for NP complete problem with the proof P equal NP. More in this to follow. If P not equal NP, the NP complete class provide a reference set of the hardest problem in NP. So most of people believe this, right? So here, the hardest problem. But if this is true, then we can find the polynomial time algorithm for NP complete problems, which till the moment, no answer. Okay, here they will start talking about polynomial time reduction. So we need to have a more formal definition. So from the bottom or the heart of NP completeness is the notion of a polynomial reduction. The idea of a polynomial time reduction is to take as a problem, like deciding if SA is the language LA and efficiently transform it into deciding if SV is a language of in LB. Okay. Assume that we have a way to efficiently sum problem A into problem B. So what? If we can turn some problem A, we can turn it into problem B. What does that mean? So we have algorithm A. We can input it to problem B, then the output from problem B in a polynomial operation output from A. We are interested in time A takes to run, not including the call to B, because if it is polynomial time, then we know that we can solve A in whatever time it takes to solve B, plus a polynomial factor. Here we have some pseudocode explanation of a reduction. Let MA and MB be deciders. Those are Turing machines for LA and LB, respectively. We can use polynomial time reduction if one exists, if there is a polynomial, to implement MA as follows. Some code transforming S into an appropriate S prime, out B, MB of S prime, call MB on S prime, some code transforming out B into appropriate out A, return out A. We say LA polynomial time reduces to LB. What does that mean? You can see where this is going. The existence of a polynomial time reduction from problem A to problem B means that solving problem A is essentially no harder than solving problem B. Why? Because if you can prove the existence of a polynomial time reduction from A to B, you are effectively saying A takes however long B takes, plus a polynomial overhead of converting an instance of A into an instance of B. Let's have a formal definition of this. A polynomial time reduction. A language A is a polynomial time reducible to a language B written A is less than or equal producible of B if a polynomial time function f of 0 and 1 star will take me to 0 and 1 star exists such that for all W, string W belong to A, and if and only if there is f of that string belong to B. In other words, F is a polynomial time reduction from A to B. If given some string W, A, you can compute X of F of W in a polynomial time, and BW belong to A if and only if X belongs to B. I know this is complicated for you. With next class's examples, it would be more clear. Because with practical examples, but there is no time today to have examples. With practical examples, it would be clear for all of you. A language B is NP complete if B belongs to NP. For all A belong to NP, and A could be reduced in a polynomial time to B. B is NP complete if it is an NP problem, and there exists a polynomial time reduction from every other NP problem to it. No, it's if and only if are there. So both conditions should be satisfied. That's the meaning of if and only if. So it should be correct from both directions. Clear? So you back to the same question. Is P equal to NP? We don't know the answer. It's it's a $1 million question. If you can prove that, they will give you a PhD and $1 million if you want to research on that. Okay. Guys, I'm showing you with the complexity and NP, P and P, complete and X. I'm showing you one of the most, or still, it's an open problem in computation. No answer yet. And this is why you should know. Because some software engineering, computer science, application developer, that they think that the computer can solve anything. No, the answer is no. There are more than 10 open problems. One problem has been solved, but the other still remain. Since the 20th century, more than 100 years, some of the problems, they are available yet, and no answer yet. What are the consequences of NP problems or NP complete? If you have an algorithm to solve an NP complete problem B in a time of big O of F of N, any other problem in NP is solvable in time big O of F of N plus a polyfactor of N. Here are some interesting consequences. If B is NP complete and B belongs to P, then P equal NP. If B is NP complete and B could be reduced in a polynomial to C and C belong to NP, then C is NP complete. If B and C are both NP complete, then B could be reduced to by polynomial factor to C, but also C is less than also could be reduced to P. But can we solve this? No. Then Coq-Levin theorem. Let's start with his definition that the Boolean satisfiability problem SAT, we call it, is defined as follows. Let phi be a conjective normal form, CNF, Boolean equation of K clauses and N variables, such that phi equal A1 or A2 or A3 and A4 or A5 and A6 or A7, whatever. SAT ask the following question. Giving phi, is there any assignment of variable A1 to AN that belong to 0 or 1 such that phi equal true? This is the question. Giving phi, is there any assignment of variable A1 to AN belong to 0 to alphabet 0 or 1 such that phi equal true? Cook-Levin said SAT is an NP complete problem. Proof. So it's in theorem 7.37 in textbook for the proof. The idea is you can you convert any problem in NP into CNF, Boolean circuit in a polynomial time. This known as the Cook-Levin theorem after Stephen Cook and Leonid Levin, who first proved this result. Those the first two who proved this result. Okay, we have Cook and Levin theorem, those two guys who proved this. So what? What do we benefit from their proof? The Cook-Levin theorem establishes SAT as the first NP complete problem by showing that all problems in NP are polytime reducible to SAT. That initial proof was the hard part. Now, if you have some new problem X and want to prove it NP complete, you only have to prove two things. Problem X is N and P, then 3 SAT less or equal in a polynomial factor reducible to X. How this would be with the example we will see. Next class. And you have a question in the assignment about this. Showing a problem is in NP is straightforward enough. Show it is a decision problem that checkable in a polynomial time. Finding a polynomial time reduction from 3 SAT to X, if it exists, if we can do that, is typically easier than showing all a problem in NP reduced to X. Thus, Cook-Levin give us a kind of toehold into NP completeness. So I think the reduction example would you like to continue our next class tomorrow? Guys, sure, continue tomorrow. Okay, Ardi and Brandon. So tomorrow we'll talk about the reduction example 1, reduction example 2, and also in the class note we'll have more examples. But the class note I will do it next week because tomorrow we'll talk those two examples in 11. Then we'll have 12. The classes NP hard, BPP. Okay, just a second. Just a second. And we'll start talking about this problem and what do we mean by optimization, knapsack problems. So I'll talk about more Turing problems and these classes. So I'm not sure if tomorrow we'll do those. Then we'll go with an example. So next, I hope that, or we might take part of next week. And next week will be revision from handout 10 to 12 with more examples. Okay, so if you have a question, please stay. If you don't, you are free to leave and see you tomorrow. You too, Brandon. Thank you, Lonji. Thank you, Chai. Thank you, Ardia. See you tomorrow. Erin, do you have any question? Okay. We reach to the end of our class tomorrow. See you tomorrow, guys, and have a nice day.